Okay, everyone. So looking at this mechanism, let's talk about rates now. So the reaction step that is the slowest step is really what determines how quickly this entire thing goes down. Okay, so for us here in this reaction, so let's say step 1, step 2, step 3, right? So when I say step 1, I really mean from this to here, right? So from this reactant to the initial product from the first reaction. The product from the first reaction then reacts to become the product from the second reaction, and etc. So the slowest step in this case would be step number 2. Okay, the reason why this is the slowest step is because this takes the highest amount of energy. So it takes a longer time to actually have a successful collision because you may have collisions happening that don't have that threshold. So number 2 is what's called our rate determining step. Okay, or I just use RDS for short. So the rate determining step is the one that takes the longest to actually have happen. So typically this is the one that is associated with your activation energy. So if we had to guess here, I would say reaction 1 and 3 are quite short, right? Very quickly done. But reaction 2 is going to take longer to do because it requires the highest amount of energy. So when you want to talk about increasing the rate of a reaction in something that has a mechanism, we have to talk about increasing the rate determining step. Because the rate determining step is really your factor that is going to essentially increase this reaction overall. It's kind of like if you've ever had, if you've ever seen someone run a relay race, okay? So there's usually 4 people. This is amazing. This is some of my best work as a teacher. Okay, so here is the start/finish line, right? So the first person will run and hand off the baton to the second person. The second person will run, hand off the baton to the next person, and then that continues until this last person really finishes on the finish line, right? So if we were trying to track how long it takes to do a whole lap, we don't really measure the individual people, right? Typically we just measure, okay, we start the timer and then we end the timer when we have the person cross the finish line. So like 1 lap, you can consider it as being like the reaction. Okay, so 1 reaction is like the lap. But the little individual people who are running their portion of the lap are like your little steps in the mechanism. So we have like 4 different mechanism steps here. So how quickly you finish the lap doesn't really depend on one person in this. It depends on the whole team. But let's say we had, this person and this person and this person are really fast. They're fast runners, okay? But this person maybe hasn't trained, they're a little rusty. They're slow. Or they're not slow. I mean, let's not put them down. I mean, they're not like really slow. They're just slower than the other people, okay? They need to train a little bit more. So when we want to speed up our lap that we're doing, the fast people have already trained. They're good to go. They're as fast as they're ever going to be. But if we train this person, this slow person, and get them to be faster, what we can do is we can speed up the whole thing. So this person is like our rate determining step. You're only as fast as your slowest step. Or if you've ever heard the term, you're only as good as your weakest link. Essentially, your rate determining step is like the weak link in the mechanism or in the chain. So by speeding up the rate determining step, we can get the overall reaction to then be faster. So, obviously we turn this frown upside down, we train this little guy or little girl, and then we're going to be much faster overall as a team. So same deal up here. If we lower the activation energy by, let's say, adding a catalyst, we've now automatically sped up this entire process because we've made our slowest step faster. Okay, so the same thing happens here in the mechanism. So whether you're looking at it in a chart or in more written format like this, so in this case, notice it says slow, fast, fast. So this first one that's slow is our activation energy step. This is the step that we need to speed up in order for that process to actually happen faster. So, and that's what's mentioned down here. So the slowest step in the reaction mechanism, in this case, it's the first step, is called the rate determining step. So when we want to speed up a reaction, we really want to look at our rate determining step. Sometimes instead of saying slow, fast, fast, you might be told what the energy value is that's required. So the most endothermic, or the one that requires the highest amount of energy to be absorbed, would be your slowest step. So let's say, I don't know, I'm going to make up some numbers, 25 joules, 6 joules, and 12 joules, right? So this requires the highest amount of energy input. That's going to be our rate determining step. Okay? Now there's one more term that you need to understand here when we're looking at a mechanism, and that's something called a reaction intermediate. A reaction intermediate is essentially the things that are in your reaction, or the substances that are in your reaction mechanism, but they're not in the overall reaction. In other words, it's the stuff you cross out. So our Huber and Haber here, that we crossed out from the mechanism, these are the reaction intermediates. So meaning they are made, they are involved in the mechanism, of course, but they are not in the overall reaction. So they're not a reactant and a final product, but they're made in between. So reaction intermediates on this chart, maybe I should clean this up a little bit. Maybe you can still follow along with me. Yeah, I'll just redo this. It's kind of getting a little messy. Okay. I forgot exactly what I had, but you'll get the idea. Sure. Okay, reactants and products. Okay, so we know here that each kind of hump is a reaction step in the mechanism. So here we have a 3-step mechanism. So remember that each step, so this is like the reactants from step number 1 and the products from step number 1. The products from step number 1 are typically used as reactants for step number 2. So look what I mean. So step number 1, we made Huber. Huber was then used as a reactant in step number 2. The product from step number 2, our Haber, was used as part of the reactants for step number 3. So it's like the reaction is being used, that thing that we're making is being used up in the next step. So that's why it doesn't really hang around much. So the reactant from step number 2, then we have the products from step number 2. But the products from step number 2 are reactants for step number 3 to get to the final product. So the little bottom of the hills, the little valleys here, this is where you find your reaction intermediates. Or the things that are made in the mechanism, but then they're used up as the mechanism continues on. So when you're doing this, sometimes I think your textbook will ask you this as well, where it'll say like, label on your graph where you would find the reaction intermediates. So it's always at the bottom of the valleys. Where would you find the activated complexes? Remember, activated complexes is where you have that in-between time. So where you have your reactants that have broken their bonds before we have our final product being made, or even product from that step. So activated complexes are essentially the jumble of atoms in between where bonds are broken. And the valleys are where we have our intermediates that are going to be used up, and they get crossed out in our reaction when we look at the overall process. All right, so now we have a term called entropy.